Project configuration, setting up core link aggregation. By the time we're done here, you will understand and configure link aggregation between core switches. Well, let's do a little concept review. Lag is all about bundling instead of blocking. And keep in mind, lag is an industry standard term. Cisco has their own term for it called Ether channel. And when you're the industry leader that is responsible for creating a lot of the standards, you get the right to name things whatever you want to name them. So let me ask you the question, how would Spanning Tree Protocol handle the above situation? We've got two switches, we'll just call them switch 1 and switch 2, connected together with redundant cable on fast Ethernet 0/1 and fast Ethernet 0/2. Those are the port labels. Well, Spanning Tree is going to identify a loop in this network because if you have a computer that sends a broadcast, it's going to cycle around the network, destroying the whole thing. So Spanning Tree Protocol will block one of those connections. Let's just say it's this one right there. Shunk. That's kind of a bummer because you might have these sitting right next to each other in an IDF or an MDF. You're like, man, if I could just splice together those cables somehow and use that bandwidth, and that's what lag and Ether channel is all about. It actually allows you to bundle up to 8 connections between your switches. And the great thing is it uses load balancing within the hardware of the switch so it doesn't slow anything down. Now, I want to make sure I emphasize this is between the same switch only. Let's say you had a scenario like this with one switch at the top, couple cables down here to this guy, couple cables down here to this guy. Lag doesn't mean bundling all 4 of these cables into one big link because you're going between multiple switches. In this case, you'd be able to create 2 bundles of 2. Lag has also gone beyond just the switch world. Servers now support this technology so that you can have a server connected to a single switch and you bundle multiple cables into one, thus giving the server more bandwidth potential. Now we're going to go and set up lag in our environment, but before we do, there's one more thing I want you to know, and that is the negotiation protocol of lag. Now what do I mean by that? I mean, we need these switches to talk to each other in some way to tell each other, hey, I'm going to do a lag with you. I'm going to bundle these 2 cables together so that we can get more bandwidth, and the other switch has to agree. Well, anytime you have negotiation going on between switches, you have to have some kind of standard that they agree to. I mean, over here you could have a Cisco switch, and over here you can have an HP switch. Since we live in a world with all kinds of different vendors, you have to have some kind of common ground for them to stand on. That's the protocol, and the protocol of choice is LACP. I don't even remember what it stands for. I would guess Link Aggregation Control Protocol or something like that. Don't fill your head with what acronyms mean. Just remember the acronym. That's the protocol that these guys will use to negotiate and say, hey, are you running in a lag connection? The other switch will go, yeah, I am. Let's bring this up. Now, there are other protocols out there. PAGP is actually a Cisco one, and that works between Cisco switches. It does exactly the same thing as LACP, and you might wonder, well, why do we have it? Well, because, again, if you're the industry giant and you're first to the game, creating a standard before there is a standard, you create your own protocols. And it just so happens in this case that Cisco kept theirs around even after the industry caught up. So if you have 2 Cisco switches on either side, you could use LACP or you could use PAGP. There's no advantage of using one or the other than the warm, fuzzy feeling that you're using a protocol that Cisco created. So those are your 2 negotiation protocols. Now I want to make sure I mention that you can turn on Ether channel and lag without a negotiation protocol. Think of that as the on switch. That is really dangerous because what you're saying to this switch number 1, you're saying this will be an Ether channel, always be on with an Ether channel, and you're relying that the administrator on the other side has also said, okay, well, this is going to be on and on. Now, of course, you're probably that administrator. You don't usually have 2 different administrators for 2 different switches. But what if you messed up? What if you forgot to type the on command under that port? Well, now you've got one side that's thinking the connection is bundled, and you've got the other side thinking it's just a normal link. Spanning Tree Protocol doesn't detect a misconfiguration here, and you could very well end up with a loop in the network. Because one side thinks it's bundling and Spanning Tree doesn't apply to block the links. The other side is like, it's just a normal link. Broadcast will flow everywhere. Boom, network explosion. That's why it's best to use a negotiation protocol anytime you bring up your lag. All right, let's take lag from concept to implementation. I'm going to implement it in 2 sections. First off, I'm going to implement it in the IDF because it doesn't impact as many people if we do it wrong. Then we'll move over to our Suite 1 switches and implement it in the MDF. So in the IDF, what I'm looking at is port 25 and 26 being the one designated as our lag. So looking at the IDF, we have ports 25 and 26 on our switches connected directly together. Now right now we're just letting spanning tree do its thing, so I guarantee you one of those is being blocked. Otherwise we would have a loop in the system. So before we go any further, let me open PuTTY and verify all our connections. You'll see me jump all over the place between command line and using the graphic interface on these switches just to keep you on your toes. Each of them have their own advantages. Now we've already saved these sessions down here, so I'm going to connect to RT-ST4 switch 1, which is going to be this switch over here on the top. Or if we're looking from a physical perspective, this switch up here. I'll click the open button and I'm sitting at a login prompt. Let me change the font real quick. Change settings, appearance, get past that 10-point font to a 12-point bold font. Click OK, apply, there we go, a little easier to see. Log in as Cisco with the password, and I'm in. First thing I want to do is verify my connections. Now there are two protocols that we can use to do that. The Cisco Discovery Protocol, since we're using Cisco switches, that's something Cisco created long ago that allows you to see Cisco devices. And then about 5 years ago, the rest of the industry caught up and released LLDP, the Link Layer Discovery Protocol. Both of these do the same thing. The output is a little bit different just because they were created by different people. And nowadays, you'll probably see more devices in LLDP's output because it's an industry standard. So the command I'm going to type, first off, is show CDP neighbors. This is one type of output that I can get, which shows that RT-ST4 switch 1 is connected to this platform of switch on GI25, GI25, GI26, GI26. That's the lag ports I was just talking about, 25 and 26. Or if you prefer the physical view, 25, 26. Now you might say, well, what is this? Well, it's the device ID. See, Cisco Discovery Protocol identifies devices by MAC address, which makes it not as friendly. That's where the show CDP neighbors detail can come into play, because that actually shows not only the model and the device ID, but also the name, the host name of the remote device, and the remote IP address. That can be really handy if you don't have some network documentation around. I'll also do a show LLDP neighbors. There's the competing protocol, if you will. You notice it's seeing a few more devices. These are just some, looks like IP phones that are supporting the LLDP protocol, and I see they're plugged into port 6 and port 10 on switch number 1. But this is the big one that I wanted to see. Port 25 on switch 1 is connected to port 25 on, right there's the host name, and I love that output a little bit better. That tells me I'm going to suite 4, switch 2, just like the diagram implied. 26, 26, same thing. Then I see my port number 28, which connects back to suite number 1, switch 1. And lastly, let's see what spanning tree is doing to these ports. I'm just going to type in show spanning tree. Hit the enter key, space down, and it shows all of the different interfaces and what's doing what. The main ones that I'm looking at is 25 and 26, and it looks like these are forwarding and designated ports. I see port 28, and that's the one that goes back to suite number 1, is forwarding, and that is the root port, meaning switch number 1 in suite 4 goes out port 28 to reach the root bridge. I know we're talking about lag, but spanning tree plays a big role of this. And you know, some of you might be surprised. You're like, well, wait a sec, I thought one of those would be blocked. Isn't that what spanning tree is supposed to do? Well, remember, when it comes to spanning tree, only one side will block the connection. So we know that these guys are both designated ports. Let's take a look at switch number 2. All right, I got PuTTY up. We're going to drop down to RT-ST4 switch number 2. Adjust the font size. There we go. We'll get logged in and do a show LLDP neighbors. All right, I'm zooming down right to gig 25 and 26, and I see that's connected to suite 4, switch number 1, just like we expected. Right there, gig 28 is connected to 52 on suite 1, switch number 2, just like we expected. Let's do that show spanning tree. Hit the space bar and get down to those ports. Now look at this. It looks like GI25 is the root port, meaning that's how this switch is getting to the root bridge. And look at 26 and 28. Both of these have been labeled as alternate ports. That means spanning tree is blocking those ports. Now again, I know we're talking about lag, but I've got to blend this together with spanning tree because it's so relevant. If I were to take my pen and draw what this really looks like, switch 2 would be connected to switch 1 on port 25, and that's the port that's active. Remember, that was the one labeled as the root port when I looked at the spanning tree output. This was labeled as an alternate port, which means it's blocked. Port 26 is labeled as an alternate port, which means that's blocked. Now, Spanning Tree is carefully watching this entire thing. So if this link went down or something like that, it would unblock this one to make sure that we could get back to the root. But it's always helpful to see a spanning tree perspective on the network. And what we see is the network looks pretty much like this by the time it's said and done. Those are the links that are active. And so by introducing a lag, we're implementing this in a bundle, which from Spanning Tree's perspective is seen as one connection. So we gain the benefit of the bandwidth on both of those links, and we won't find ourselves fighting against Spanning Tree to block one. So I'm going to jump to the switch graphic interface to configure the lag ports. Then we'll come back to the command line to see which commands it used. A lot of times, if you're new to command line management on a switch, that's one of the best ways to learn it. We'll start off on switch number 1 in suite 4. That's .242. 10.225.1.242. Get logged in. Enter. And jump over to port management, and right there's our link aggregation lag management. And what it looks like this switch platform has is a whole bunch of lag ports that are yet to be configured. So what this tells me is this platform supports a maximum of 8 lag ports. Now that's not interfaces in a lag port, that's lag ports, ports bundled together in a group. So let's click on lag number 1 and click on edit. First thing it's asking for is a name. We'll name this one Suite 4 Lag. Not sure if it'll let us use spaces and parentheses, but I'm going to try. Typing in switch 1 to switch 2. Now right there's a big checkbox. Do you want to enable LACP? That's the negotiation protocol to make sure that both sides agree that a lag is running. Then it's going to ask us what interfaces do you want to include in that lag. Looking back at the diagram, it looks like port 25 and 26 will be bundled together. So 25, hold down shift, select 26, boom, they're the lag members. Apply. Now it says success. To permanently save your configuration, go to here. We'll get to that at some point. And right there I see that the name has been taken and it is enabled. Now the link is currently down because the other side isn't configured. So let's open another tab and go to 10.225.1.243. That would be switch number 2. We'll get logged in there and do exactly the same thing. Port management, link aggregation, lag management. We'll choose lag number 1 and hit edit. Select LACP to enable that. And we'll name it the same thing, Suite 4-lag, and we'll put this one, Switch 2 to Switch 1. Drop down and grab those interfaces right there, add them to the lag, and apply. We'll close that window, and this is good. Take a look at this. We've got a functional lag 1. It shows the link up, LACP, the negotiation protocol, is enabled, and we have both of these ports that are considered active members. It's also worth mentioning that it's going to be using the MAC address as the load balancing algorithm. See, we now have 2 switches that are connected with a bundled set of ports. The way that it uses the bandwidth is by sending different MAC addresses across different links. So when computer A up here talks to computer B down here, it might use the left connection. And when computer C talks to computer D down here, it might use the right connection. And that's the way that lag ports work. There's no 2 sets of devices that will ever see 2 gigabits per second of throughput if these are both 1 gigabit per second link. But it will hope to achieve that level of throughput by sending and load balancing different devices over those different connections. The last thing I want to do is I want to check out what Spanning Tree looks like now. So I'm going to telnet into the switch. I'll do Cisco, type in my password, and let's do a show Spanning Tree. What do I see? Look at this. So take a look. We've got gigabit 23, 24. Where's 25 and 26? They're gone. And they're replaced with this guy right here. That's port channel 1. And that is considered a designated port. That's just a port that is forwarding. Right above it, we see gigabit 28, which is the root port. That's the port that the switch uses to reach the root. Now, does that make sense for us? This is Suite 4, Switch 1. Well, yeah, it does. That's this switch right here. So it's saying port 28 is the root port. That's because this guy right here, actually, I almost crossed it out. He's the root bridge. So it's saying I go out that port to get there. This port, which is now considered port channel 1, is designated, which means it's forwarding. Now, what do you want to bet? If we go down to switch number 2, this will be marked as the root port. You know I'm not going to leave you hanging. Let's do it. Let's telnet in. I'll do a show Spanning Tree, and boom, right there. I just had to stare at it for a second. That's the root port. Port channel 1 is the root port. That's where it's going to go. Look at the one right below it. Gigabit 28 is the alternate or the blocked port with Spanning Tree. Looking back at the diagram, does that make sense? Yes, it's going out the higher bandwidth port through that switch to get to the root bridge. This one is going to be blocked as the alternate. More on that when we get into spanning tree. It's just lag and spanning tree are so closely linked. I wanted to already be planting those seeds in your mind. The last thing I need to do is go configure these switches in Suite 1 for the lag on their interfaces. Since it's exactly the same thing, I'm going to go do that behind the scenes. Now, I said at the beginning of this that we will understand and configure link aggregation between the core switches. So here's what I want you to do. Configure lag or ether channel, depending on which term you're using, between the two core switches in your lab environment. Ensure a lag negotiation protocol is used. We used LACP in this implementation, but you can also use PAGP, which is the Cisco flavor, if your switches support it. The only other thing I want to mention before I let you go is VLANs. I'm going to do an entire series just on VLANs. They're that big, but I know some of you have already jumped into the VLAN world. If you've configured VLANs on your switch ports, you actually have to remove that configuration before you implement the lag, and then add the configuration back in on the new virtual interface. Let me explain. When you create a lag, it actually bundles the two physical ports together and creates this new virtual interface called port channel 1 or 2 or whatever number it's going to end up using. That interface becomes your new virtual interface that represents the configuration of all the ports that are in the lag. So if you're setting up VLANs, you configure them under this port. It's known as a trunk port. As a matter of fact, once you've set up the lag, all configuration goes under this interface. You don't configure anything under the physical interface anymore. As a matter of fact, if you do, it messes up your configuration and that physical interface will fall out of the lag because the lag relies on everything being identical between these two interfaces. I mention that only because I know some of you are doing this in a production environment, and removing the VLANs from the interface will cause some network downtime while you're implementing that lag. So you'll want to schedule that after hours. Well, that is core link aggregation. I hope this has been informative for you, and I'd like to thank you for viewing.